Hello everybody and welcome back to another one of my videos. This time round I'm going to be taking another look at the digital signal processor on the replica motherboard, the AA3000 Plus. And you might have joined me in my last video about that. Back in that I programmed up the DSP chip so that it would do the calculations behind the Mandelbrot set, producing all those pretty sort of chaotic pictures. But to be honest with you, after I'd done that video I was just a little bit disappointed that the DSP wasn't shining as much as I expected to compared to the 68000 series CPU. Yeah, okay, the 68060 is a pretty mighty chip, but surely the DSP ought to have shown a bit more metal against that CPU. So I've been working on the program in the meantime, and I thought it would be helpful and interesting just to show you a brief update on where I've got to with that. Just as a reminder, if you enjoy the videos you're watching here, don't forget to hit the subscribe button down below and you'll get a notification when I bring out my next video. But let's just do a quick reminder of where I got to in the previous video, and there I had cheated and had to turn off the data cache. So let me do that again and run the DSP program as I had it at that time. And here it is. So this at the moment is the floating point unit doing all the sums, the floating point unit on the 68060 chip in my Cyberstorm Mark II accelerator that I've got in the computer. So there it is, chugging its way through the calculations relatively slowly because I've turned the data cache off, but still it does all the sums, and certainly does all the sums a lot faster than the onboard 68030 would do. 35 seconds. If we turn the CPU cache back on again, that would take something like 9 or 10 seconds to run. But that's the FPU. This video isn't really about the FPU, it's about the DSP. So let's just hit the D on the keyboard and get the DSP to do the work. And there it is, drawing the picture. This is what we looked at last time round. And what is going on here? Well, what happens is, as I explained in the last video, think of this as a sort of map grid, latitude and longitude, perhaps coordinates of each of the points. The 68000 CPU works out the coordinates of each pixel on the screen, sends those coordinates to the DSP chip, says calculate what the colour ought to be for that pixel, and then tell me the answer and I'll colour in the screen for that colour. And there we go, DSP took 33 seconds. So that's considerably slower than the 68060. If you zoom in a bit, then the DSP disadvantage, so to speak, that the longer time it takes is reduced compared to the 68060. But this doesn't seem to be a sort of shining example of the DSP. And you know, why is that? Well, there are a couple of reasons, but let me talk about the first one, which was the first hurdle that I overcame, and that is, for each pixel on this screen, what happens is, under this version of the Mandel program, the CPU tells the DSP the coordinates, DSP does its calculations and then returns with the colour value. But that overhead of passing information off to the DSP and then getting it back again adds quite a lot of time overhead in calculating each pixel. So that was the first thing I had to think about, and it occurred to me that the way this Mandelbrot program works, as we saw, is to calculate in columns. So why not tell the DSP chip the coordinates of the starting pixel in the column and then let it work out the values for an entire column and fill in that in a place in RAM. Just fill in the values for an entire column, then return to the CPU to colour in an entire column at a time. And if you did that, of course, because you're not you're only calling the DSP once per column, you're reducing the overhead by, in fact, 256 times here, because there's 256 pixels vertically. So that is what I did in not version 1.61 that we were looking at there, but version 2.5. But before I call that, let me turn the data cache back on again, because version 2.5 works with the data cache on. So let's run that. So again, it always defaults to using the 68060, this time with the data cache on, so it's running a lot faster. Look, there we are, 9 seconds. But now let's have a look at the equivalent calculated for an entire column using the DSP chip. And already that looks a lot faster than it was before, and you can probably see that rather than stuttering over each pixel, actually we're tending to get a column at a time here, because the 060 can paint in each pixel in a column one after another. There are 14 seconds, so we've closed the gap quite considerably on the 060, but we're not there yet. What else can we do? Well, I did mention before that there were two things holding up the DSP, but I only talked about one of them, so let me come back to the second one right now. And that is that this version of Mandel that we're looking at here and the previous version both have the DSP program running in the shared memory of the Amiga system, in fast RAM in other words. But the DSP chip on this computer actually has some onboard RAM that we can make use of. And you know, why bother? Well, the advantage of that is it is invisible to the rest of the Amiga system, so any program running from that DSP RAM can access the DSP RAM without interrupting the rest of the Amiga system. In other words, the rest of the Amiga, the CPU, can carry on processing even when the DSP is doing something else internally. And if you like, you can have two programs running at once, one on the DSP, one on the CPU, absolutely in parallel without slowing each other up, as long as they're not accessing that shared memory. And if you like, that's a little bit like maybe the Blitter and the CPU. They both access shared memories, chip RAM in other words, and provided they're not both trying to access chip RAM at the same time, then they can both run programs successfully. It's when they're both trying to operate on the same chip RAM that you get contentions. So, okay, at least that makes some sort of sense, doesn't it? Let's instead locate the DSP program on the DSP's memory. So what does that mean? It means the program's running there. It means some of the sort of interim values that it's calculating that it needs to store somewhere, sort of scratch pad values, sit on the DSP RAM. When it calculates a column still, well, it has to save those answers somewhere that the CPU can get hold of them. So that still has to be back in fast RAM. You know, if all we do is calculate a column of values by the DSP, maybe a little bit quicker than before because that's done in the local DSP RAM, but then tell the CPU to paint them, then the DSP sitting there doing nothing while the 060 is just putting them on the chip RAM screen here, and then the DSP goes again with the next column. So we'll get some sort of speed up, but it won't be that great. Actually, doesn't it make more sense to interleave columns and look at a pair at a time? So actually what we'll do is we'll get the DSP to calculate two columns, column 1, column 2, and then while the DSP is calculating column 2, the CPU can be filling in column 1 on the screen, and then when those are ready we can move on a set. So the CPU could colour in column 2 while the DSP is calculating column 3, and then 3 and 4 and 4 and 5. So to work in pairs of columns with the two processors actually working on different columns at the same time. So to do that we need two buffers, one for each column, but if we just make the necessary program changes for that, then actually in theory, at any rate, the DSP could be working on one column while the CPU is working on the other one. So that sounds great in practice, or in theory rather, but in practice, you need a little bit of coordination between the two processors. You don't want them tripping up over each other, so that needs a little bit of care, but that is what I have got at least partially working in the latest version of the program. So without faffing about anymore, let's just have a look at that. So once again we default to the floating point unit on the 68060, and that's at the same speed as it was before because none of the program has changed. But let's have a look at the DSP in action. So I hit D on the keyboard and wow, look at that, 2 seconds to calculate the same thing. This thing rocks. That's 5 times faster than the 68060 was, and that's no slow chip in its own right. Zoom in a bit, 4 seconds. Where should we go? Let's follow this little corner piece up here. 4 seconds. It doesn't slow down markedly even when we're zooming in. This thing is really quick at what it's doing here. So that's probably as much performance as I can squeeze out of the DSP chip. What it's shown to me though is if you can be careful in the way that you code things up, and that you make sure that the DSP is running as much as possible in its own RAM space and only passing values back and forth to the CPU when it absolutely has to, you can get some serious performance out of this thing. I mean, imagine this program having come out on a computer that had been launched in the early 1990s or something, with a 68030 processor on it. No one had 68060 accelerators in those days. 68030 CPU, which probably would have done the colouring in process and everything at a similar pace to the 060, maybe slightly slower, but the DSP would have blown everybody away at that time, being able to draw Mandelbrots this quickly, way faster than any regular solution at the time. Even with this FPU chip added on the side to 68030, that would have been a 68882 at best, and it wouldn't have got anywhere near this kind of pace. So seriously impressive, and what a shame Commodore didn't follow through with the AA3000 at the time, because that really would have been surprising to have seen this kind of thing running back then, but it wasn't to be. So we are left with it as a bit of nostalgia instead. But hopefully that's shown what might have been possible from the DSP chip. I think probably got towards the end of the line with this program now, subject to any final little bugs that need ironing out. But I hope you've enjoyed having a look at that, and just a sort of indication of what is possible with the DSP. So I think that's time to wrap up this video. As I say, if you enjoyed it, don't forget to hit the subscribe button, and join me next time when we'll be looking at another aspect of retro computing. That's it for now. Thanks for watching. Bye.